Today's video, we're going to talk about Le Chatelier's principle and what happens when you make changes to a system at equilibrium. So essentially, what's going on here is that whenever a system is at equilibrium, then if you make adjustments to it, it will no longer be in equilibrium. In other words, the rates of the forward and reverse reaction will no longer be equal. So one of them is going to be faster than the other, and that will drive the reaction in the direction of the faster reaction. So that's what's happening in that case. And so it'll return to equilibrium. Now, some people think it's magic or that the reaction can think and then it just knows which way to go. But it's really, again, just collision theory. The faster reaction makes more products than the slower one. And so it returns to equilibrium. And eventually both of them have the same rate again. So it looks like the system is thinking and opposing your will, but it's really just doing what science does according to collision theory. So the system will oppose the change that you make and return to equilibrium. So just remember, it's going to react by undoing the thing that you do, not because it's mad at you or because it's smart, but just because of the way chemistry works and kinetics and all those principles that we've talked about already. So there are three ways you can change a reaction that's in equilibrium. You can impact or mess with the concentrations of the reactants or products. You can change the pressure. Now, you can also change the volume, but changing the volume is really just changing the pressure. So if you make the volume smaller, the pressure gets bigger. So a volume change is really a pressure change. Or you could change the temperature. So let's look at each of these three changes and see if we can tell what's going to happen. Whenever you introduce something, then the system will respond by trying to take away the thing that you introduced. So if I put more of a reactant in, that's going to make a higher concentration, which means the rate will go faster. So that reaction goes faster for a while until you use it up. And then as the reactants get used up, the concentration goes down and the rate goes slower, and eventually you get back to equilibrium. So the way to remember it is that it's going to oppose adding something. So it's going to use up what you introduce. And then if you take something away from it, it's going to respond by regenerating that. And it's all going back to rates of reaction. So it kind of does the opposite of what you do. So if we look at the process for the generation of ammonia, under normal conditions, this reaction doesn't really work. But if you manipulate these variables, temperature, pressure, concentration, then you can produce ammonia from the reaction, and that's exactly what we do. So you can see it's an endothermic process. Here's the balanced equation. Let's take a look at what is going to happen if we change the concentration. Well, what if we add hydrogen? If we add hydrogen to this, then that's like increasing the amount of reactant. So this concentration is going to increase. And we said it's going to oppose the change that we make. So if we make this concentration bigger, it's going to want to decrease the concentration. The way to decrease the concentration of H2 is by doing the forward reaction, because the forward reaction consumes hydrogen and nitrogen to make ammonia. So by increasing the concentration of H2, it will favor the forward reaction. Okay, so what if we add ammonia? Well, if we add ammonia, now we're increasing something on the product side, and it's going to respond by trying to decrease that. And the way you decrease that is to do the reverse reaction, so that ammonia gets used up and nitrogen and hydrogen are made. So adding ammonia will favor the reverse. Notice in both cases, it goes away from the side of the thing that we add. Now, it should be noted that in this reaction, there's no side to a reaction. If it's in like a beaker or a container or something, all the reactants and products are just swimming around in here together. You can't add a substance to the reactant side or add a substance to the product side. All you can do is add something to the reaction mixture or take it out. So don't talk about adding and removing from a side, talk about adding and removing from the reaction, and then you see which thing is favored, either products or reactants. Okay, and then if you were to remove something, then if I come back and now we're saying, you know what, I'm going to take nitrogen out of here. Well, the system is going to oppose that change as well, and it will oppose it by trying to make more nitrogen to put back what you took out, and that involves the reverse reaction. So removing nitrogen will cause the reverse reaction to happen as well. So those are the concentration changes. Really? I have to do that? Well, that's fun. Maybe I don't want to write on this. So what if we go back to this equation again, and now instead of manipulating the concentration, we want to change something else. So the other possibilities that we had were temperature and pressure. So let's take a look at those changes as well. Okay, so if we increase the volume, well, we said volume was really like pressure. So if we increase the volume, that's really going to be like decreasing the pressure. So that is the same as the pressure going down. Now, here's the deal with pressure. If you lower the pressure, it's going to want to increase the pressure to undo the change. So what you have to do is count how many moles of stuff you have on each side of the reaction arrow. Over here we have 4 moles of gases, 3 plus 1. Over here we only have 2 moles of gases. So if I drop the pressure, the way to get more pressure is to go where there's more stuff. So if you lower the pressure, it'll go towards more moles of gas, which in this case is the reactant side. It's not always the reactant side. You have to count in this particular example, lowering the pressure will cause it to go towards reactants because more stuff, more particles means more collisions, which means more pressure. Well, what if we were to increase the pressure? When you increase the pressure, the system will want to undo that change. It will want to oppose it. It will want to lower the pressure. And to lower the pressure, you have to go where there are fewer moles of gas. So in this particular example, it's going to be the product side. Going towards the products or to the right will generate fewer particles because we're going from 4 to 2 moles. And fewer particles means fewer collisions, which means lower pressure. So still opposing the change that we make. If we add it, it goes away from it. If we take it away, it goes towards it, whether it's pressure or concentration or temperature. Now here, this one's a little weird. You add helium. Well, there's no helium in the reaction, but it's still a gas and it's still particles. So it's still going to cause pressure. If I put helium into the container of all these gases, there's more gas, there's more collisions, there's going to be more pressure. So adding helium is really like a fancy pants way of saying we're going to increase the pressure. And we know in this case, when the pressure goes up, we go towards fewer moles of gas. Well, we always go towards fewer moles of gas. In this case, that means going towards products. So that's pressure. And if you get a volume, just make it the opposite and call it pressure because a bigger volume is a smaller pressure. and vice versa. And so that means the only thing we have left is a temperature change. So let's take a look at our temp change and see what happens if we make that sort of modification. So here's our same equation again. Now we want to change the temperature. Well, what's going to happen if we increase the temperature? To do this kind of problem, we need to look and see where the energy term is. Here, it's a reactant, so we know it's endothermic. Well, you just find where it is in the equation and you treat it like any other reactant or product. So think of this as your temperature, the energy term. If I'm increasing it, then it's going to want to undo that change. It's going to want to decrease, so it will move away from the side that the heat term is on to decrease the temperature. So this will change depending on whether your reaction is endothermic or exothermic. So don't think about it like that. Just think about increasing means away from the heat term, whether it's on the reactant side or whether it's on the product side. So in this case, if you decrease the temperature, it's like you're taking this away. And the reaction's like, well, wait a minute, I wanted that much energy. I need to make more, so it opposes the change. It's basically like a teenager, you know, you go in and clean the room and they're like, hey, now I can't find anything. I wanted it that way. You don't clean up and they're like, how come you left this so messy? You cleaned your room, why didn't you clean my room? So, you know, pretty much they're just never happy. It's like this. They're just difficult. They just oppose everything. All right, so a couple of other notes on Le Chatelier's principle. When you change the temperature, the value of the constant changes. That's the only one of these changes that will impact the value of K. Not changing the pressure, not changing the concentration, only changing the temperature. A new temperature is a new K. So if you look at this example, I have like a goofed up equilibrium expression over here. Some of my font stuff worked out kind of goofy. So if that equals that, and we got products over reactants, then you can see that this is exothermic, or sorry, endothermic, because the heat term is a reactant. And so if you're doing products over reactants and you increase the temperature, Le Chatelier's principle says that if you increase this, it will move towards products. And so if we have a bigger number up here, then we're going to have a bigger value for K. So it might seem counterintuitive, but when the reaction is endothermic and you increase the temp, K gets bigger. And you can determine that using Le Chatelier's principle and your equilibrium expression. So here's your K at 273, a bigger K at 298. So Bichat's principle works great for determining what happens to the value of K when there's a temperature change. Notice that with a catalyst, K does not change, but we know a catalyst makes the reaction go faster. So you're just gonna get to equilibrium faster. Same K, get to equilibrium sooner.